Um, this is kind of what we're going to be doing today. We're going to review the homework. I'll have that up in a second. I'm going to give you some notes on uniform circular motion. We'll start some practice problems together so you get a good feel for how those problems work. And then I'm going to give you for homework and time in class to work on additional practice problems, not many. And then we also have a lab that's an inquiry-based lab that you need experience with. This is a lab that shows up often in AP exams. And since you're not here on campus to do the lab, I've recorded for you what it looks like. So you'll have the recording, you've got the lab document. It's not going to take a lot of time at all. It's just a good experience to take a look at. So that's where we are, where we're going. And let's take a look at the homework. I've already got one request for number 5 in the homework. That's totally cool. Let me get my pencil out. I'm already sharing my screen, so we're in good shape. Move all this stuff out of the way. All right, so number 5 we'll definitely look at. I've had a lot of questions about 6, 10, and 11 in other classes. So if we have the same questions here, I want to make sure we address them. So the first one, all right, I got 5 and 10 showing up in the chat. All right, 10, 11, 7, 5. Okay, don't let me lose track of those because if the chat builds up, I'm going to lose track. So make sure you become audible too if I move too quickly. All right, I'm only looking at 5 right now. What I'm going to do is, since they already give us the answers in this worksheet, let's look at the keys to the solution or the strategies behind how to solve them. If we can get the strategies and we see the answers, we're on a good path. All right, so let's look at 5 first. Here they've given us, let's let the speakers.
In the cafeteria and gym are released to go to their 4th period class.
I'm sure those students are looking forward to that. Okay, so we've got Earth with a mass. It orbits the sun with a mass. We have the radius of that orbit. So we have 2 masses in a radius. What we could use is the force of gravity is equal to the gravitational constant times a mass over a distance squared. That gives us force of gravity. That force of gravity is our centripetal force. Centripetal force is simply the forces that keep us in a circle, and that gravitational force that is felt between the Earth and the sun, that is its centripetal force. So I'm going to circle force of gravity, and I'm going to say it goes to centripetal force. So we have an FC. The question it asks us to do is find what? What is the centripetal acceleration? Well, that's awesome because we know that acceleration, let's see, well, centripetal force is equal to what? What is the centripetal acceleration? We have mass times acceleration. So if we divided by mass, would that get us the acceleration? We have the mass of Earth. If we've solved for the centripetal force and we have the mass, couldn't we divide by the mass? So simply divide both sides by m, get us there. That's one method. Another method too is that we can say that that's one way of doing. I'm gonna kind of draw a line and say, well, what if we didn't want to do it that way? What if there's a different way about going about things? Is there anything else we could have done? Yes, there is. We can say that acceleration is equal to velocity squared over radius. And velocity is equal to 2 pi r over period. If we were to take what velocity is and replace it in the acceleration equation, we would have acceleration is equal to 4 pi square r over t squared. Now, do we have enough information to solve this equation? It's a rhetorical question. I'm going to answer it for you. Yes, we know what 4 is. We know what pi is, 3.14. Radius, they told us the radius to that rotation or that circular path, that circular orbit. But the period, do we know the period of the orbit of the Earth around the sun? Isn't it 1 year? And couldn't we take that 1 year and break it down into the number of seconds in a year? Yeah, I mean, 365 days, 24 hours, and then 3,600 seconds in an hour. So we could do it either way because we know the period. Now, if it was talking about a planet that we're not sure how long it takes to orbit the sun, that's a different story. But we could have used either of these 2 strategies in order to solve this problem. And both of them should have come up with an answer very similar to, if not the same, that they gave us. That's the strategy for number 5. Don't worry, this recording, could we try the first method? Yes, you can absolutely try it. Go for it. I'm only giving you the strategies. They gave you the answer. I'm giving you the strategies. It's up to you to walk through it. If you struggle to walk through it, meet me in tutorials, meet the other teachers in tutorials. But since this is just the review, I want to go quickly because we got new material, but I have no problem. All right, I'm going to scroll up. We had 5, 10, 11, 7. Okay, so 7 was the next one in that row. Okay, let's take a look at this. We have a mass. I'm going to put the given off to the side for some of these. So I'm going to say mass equals 1,000 kilograms. Around a curve which has a radius. Okay, so radius equals 50 meters, and coefficient of friction equals 0.3. How fast can the car travel around the curve without sliding? Okay, so it's asking about velocity, right? So if it's asking about velocity, we know that we have to have an equation that solves for velocity. They gave us a coefficient of friction, and so I'm going to tell you that a car staying in a curve, the centripetal force is friction, because if we were to put ice all over the road, it wouldn't be able to take that curve. It's going to slide right off the road or keep going straight or something. So we know our centripetal force is equal to the force of friction. We also know that the force of friction is equal to the coefficient times force normal. In this case, a car, well, in every case, a car doesn't accelerate vertically, it accelerates horizontally. And for that, we know that force of gravity and force normal for a car are balanced, because we have balanced forces in the vertical for a car. It doesn't accelerate vertically. That means force normal, this guy right here, is equal to mg, because they're balanced. So we could say that force of friction is equal to the coefficient 0.3 times the mass 1,000 times gravity of 10. If I don't have a calculator right in front of me, actually I do. Well, 0.3 times 10 would be 3, times 1,000 would be 3,000. So force of friction is equal to the centripetal force, which is equal to 3,000 newtons. Okay, so we've got our centripetal force, and we know that centripetal force is equal to, actually I'm explaining this more than I did the other one, my fault. But this one I kind of felt like it wasn't that much to do. All right, so centripetal force is mass times centripetal acceleration. Centripetal acceleration is equal to VT square over R. So we could say centripetal force is equal to mass times velocity squared over radius. In this case, we have solved centripetal force here. They gave us the mass right there. Radius, they also gave us right there. So we have everything we need except for velocity, so we could solve for velocity. So that's going to be our strategy for number 7. All right, so number 7, I have 9, 10, and 11 on the list. What's crazy is most people ask, y'all are the only class that didn't ask for 6. Okay, let's get through these quickly so that way we can get onto new material, and the late students can make it into class as well. A cord holding a 0.4 kilogram ball. All right, so mass equals 0.4 kilograms. We'll break if the tension. All right, so tension is my, this is tension. Let me write this a little bit differently. So I don't want you to confuse it with the period. So what if I do like force of tension is equal to centripetal force, which equals in this case 60 newtons. How fast can the ball travel? So we're looking for velocity. If the radius equals 1.3 meters. Well, we know that centripetal force is equal to mass times acceleration. And if we replace acceleration with what it breaks down into, or its formula, mass times velocity squared over radius. Well, we have centripetal force, we have mass, we have radius. Now we could rearrange and solve for velocity. My preference would be you would break this down. You'd multiply both sides by r and then divide by m. So you would have force times radius over mass square rooted equals velocity. That's your formula when you rearrange it and solve for velocity. Okay, I'm gonna hit 10 and 11 pretty quick. 10 is gonna be like the first one we did, was that like number 5 or something? Our force of gravity is going to be equal to our centripetal force. What are we looking for? The radius. Let's see. What is the velocity? Okay, we want the velocity. So if we use Fg is equal to g times m over r squared, they've given us enough information in order to do that, haven't they? They have the mass of Mars, the mass of the sun, and the radius. Okay, so we can get force of gravity, which is our centripetal force. We know centripetal force is equal to mass times acceleration. We're looking for the velocity, so we've got to change it to where it shows velocity, which would be mass times velocity squared over radius. So we've got Fc, we solved for that through force of gravity. The mass here would be the mass of Mars because it's the velocity of Mars, and we have the radius. We would simply rearrange the formula like we did in the previous problem and solve for velocity. Number 10 is going to be like the other one that we did for friction. It's similar. Gives us coefficient of friction in the car, the tires, and all of that. What we can do is we can say, well, force of friction is coefficient times force normal. This is a car, so force normal and force gravity are balanced. So we could say force of friction is coefficient times mg. Since friction is the centripetal force in this problem, force of friction as the centripetal force is equal to m times ac. I'm worried about these two. Force of friction is mu times mg, and it's mass times centripetal acceleration. We know that because, well, force of friction is mu times force normal. There's no vertical acceleration, so force normal and force gravity are in equilibrium. They're balanced. Force of friction is our centripetal force, and centripetal force is mass times centripetal acceleration. We can set these equal to each other. Mu times mg is equal to mass times ac. Masses cancel. We know what g is, it's 10. We could solve for acceleration off to the side and say, well, this is vt squared over r. What did they give us? They gave us r, they gave us v. We could use those values to get what AC is and then divide the 10 over and we would have the coefficient. Those are our strategies for this. Yes, I went by it quickly, but you can play this recording back. This will be the one that I post. If anything doesn't make sense, you can certainly email me or tutorials. Okay, so I'm going to stop the share on this one since we went through roughly half the sheet. Well, roughly. I'm going to stop the share and then I'm going to let's address anybody that's in the waiting room. So,
Mr. Watley?
yes.
So I know the answer is next to the problem, but when I went through and tried to solve for the coefficient, I got a completely different answer using the same process.
Okay, how close were you?
Mine was like 0.7 off. Like I got 0.13 and the answer is 0.84.
This was on number 11?
Yeah.
Okay, so the reason that they have 0.84 is because they use 9.8 for gravity and you're using 10. So that I wouldn't worry about. As long as you have the strategy in place and the same mechanism, you're fine.
Okay.
Okay, everybody that was in the waiting room is now in the Zoom. I'm going to start beginning our class as soon as I get the initial people here that are in the waiting room. So if you make it to the waiting room by class time 2:55, you will be in the class on time. If you come in late, you're going to have to wait till I take a break from teaching. It's become way too disruptive for you to just roll into class 2, 3, 4, 5, 6, 7, 8, 9, 10 minutes late and think that that's acceptable. It's not. If you were on campus, you would be walking in with a tardy slip, but we want to abuse the system because you're sitting at home in front of your computer. Class starts at 2:55. If you want to take advantage of being in class and having the advantage of being able to ask questions and get help, you need to be here on time. Otherwise, just relax and I'll get to you when I can. If you're going to come to my class really nonchalant and say, I'm going to show up when I show up, I'm going to admit you when I admit you. You don't need to text anybody. You don't need to email me. You just need to sit and wait patiently. Okay. Let me see, for those that were asking, let's see, number 9 with the first strategy, I got centrifugal at 5 points, but then when I use the second part, I got, which is correct. I don't know if I messed up. Let's look at that one once we get through everything and come back to it. I don't want to dwell too much on the homework, but I do want to come back to that one and look at it with you. So don't let me forget though, because I totally will forget. So when we get to a point where you're working on work, remind me, we'll look at that one together. What I want to do now, switch gears and look at notes for circular motion, but instead of horizontal, now it's going to be vertical. And the difference is now that it's a vertical circle, we've got gravity, because gravity works in the vertical. So let's switch back over and let's do some notes. There we go. All right, so let me draw a shape so we can start with the big fat circle. And let's go with, there we go. That's a pretty big enough circle. And if we draw, let's draw black on it. All right, so there's 4 points that I'm going to use on this circle to highlight what we're talking about. Let's say what would be the 12 o'clock, maybe the 6 o'clock, 3 o'clock, and 9 o'clock portions. All right, like if we're looking at a clock, this is a vertical circle going up and down. If we're at the top at the 12 o'clock position, we know that centripetal force is an inward directed force. And we know that gravity is downward as well. Force of gravity goes down. I'm going to mark it as mg because that's how I solve it. If we go to the 3 o'clock position, inward force, centripetal force. Gravity, still in downward. If we go to the bottom 6 o'clock, centripetal force upwards, gravity downwards. Yes, top drawers of those. I've got the hangy things and the folders depending on which one you go into. Have as many as you want. I'm not doing folders this year, so I've got, yeah, I've got, those are those dividers for testing that we used to use. Oh yeah, there's tons, as many as you want. Oh yeah. I'm trying to do everything digital, so you're welcome to them. No problem. Oh, you're fine. You're fine. Totally cool. The struggle is real. If we looked at the 9 o'clock position, we know what's that? It would go in. It goes into the center. Center seeking force, centripetal force goes towards the inside, and then gravity, we all know, goes down, mg. Yes, centripetal acceleration still exists. It points inwards. Yes, velocity is still tangential, just like it was before. I'm just drawing the forces so that you can see for your net force, okay? All we're looking at is centripetal force is the same, centripetal acceleration is the same, velocity is the same as last class, okay? But since I'm gonna make some comparisons and utilize mg as a force, I wanna make sure I'm drawing the corresponding forces, which would be the centripetal force. We know centripetal force is any force that keeps you in that circle as you go around it, okay? So we've got a collection of possible forces for centripetal force. It can be friction, normal, force gravity, tension. Those are all potential centripetal forces. And then gravity is pulling you down, okay? If we're looking at these, let's talk about the top point first, the uppermost point. So let's just title this top for no other reason except for, well, that's where it's at. Here we've got gravity is acting in the same direction. So let me just write gravity, same direction as, ooh, that was an ugly S, as FC. So centripetal force, gravity, same direction. If we look at the bottom, gravity, opposite direction as centripetal force. Okay, so when we're doing our summation of forces, on the horizontal, gravity was perpendicular. It didn't count. It didn't matter. No one cared about it. It's like the step sibling that you never really wanted. Just kidding. You love all your family, no matter who they are, sure. But in this case, before we had centripetal force as mass times centripetal acceleration, but now we've got another force to go into our net force, right? At the top, we have FC, And mg is going the same direction, so plus mg is equal to mass times centripetal acceleration. On the bottom, not too much different, Fc minus mg is equal to MAC. If I'm going to solve these equations for Fc, so I can say Fc equals something, centripetal force is equal to what? Solve for Fc. Well, I'm just, on the first one, I'm going to subtract it over. I'm going to say Fc is equal to MAC minus mg, because I'm subtracting it to the other side. For the bottom, the 6 o'clock position, Fc is equal to MAC plus mg. I just simply add it to the other side. And remember, MAC, that's mass times centripetal acceleration. Mass times acceleration. Newton's second law, right? It's just simple, nothing complicated. We haven't gone wild and crazy yet, but we might. So I'm gonna get a drink of water and digest everything we just talked about. It's pretty heavy, right? Okay. Now, you guys ever gone on Six Flags? You ever driven by Six Flags? You ever heard of Six Flags? Maybe Disneyland, Disney World, Busch Gardens. I don't know. I'm running out of places. When you're on a roller coaster, unmute real quick because I want to hear at least like 5 voices. Unmute, unmute, unmute. Okay. Is it the top or the bottom that you feel like you're going your fastest? We're on a roller coaster, the top or the bottom?
The bottom.
Bottom. All right. At the top or the bottom, where do you feel like you're almost going slow, or you might get a feeling of weightlessness?
Top.
The top, right? As you come across the top and you're coming around, you might feel weightless at the top, or you might be going slower at the top. But at the bottom, you definitely feel faster, right? So if we're going to solve for velocity, the highest velocity, where would we want to solve for the maximum velocity at, top or bottom?
Bottom.
Bottom. So what we're going to do is, you can mute back. I won't keep going around with this. So mute back up. If we want to say where the maximum velocity is, we want to solve that at the bottom. We know that because that's where we feel the fastest. So let's do this. Let me draw a line straight through so I don't get confused. Doesn't get confusing. So draw a line here. Excuse me. VT is maximum at the bottom. And this is supposed to be an at symbol. It confused somebody earlier and they were like, what is that C? It's like, what's C? I don't see a C. If VT is maximum at the bottom, let's look at what that equation was. We said it was FC is equal to, what did we say? MAC plus MG? It's right there, right? MAC plus MG. Well, if we're talking about velocity, we're not talking about acceleration. We're talking about velocity. So I want to get rid of that acceleration and plug in what velocity is. Remember, acceleration is equal to velocity squared over r. So we would just change this to say FC is equal to mass times velocity squared over r plus mg. And I can make this look a little bit nicer where I make my FC nice and big, where it's like FC is equal to all that, right? I haven't changed anything as far as gone wild and crazy. I've just replaced acceleration with v square over r, vt square, tangential velocities squared divided by radius. Now, if someone wanted us to solve for velocity, we just need to rearrange that. Wait, we cannot calculate velocity at the top. Can we not calculate velocity? We can calculate velocity at the top. We'll totally get to that. This is for maximum velocity. Maximum velocity is going to happen at the bottom. Maximum velocity. If you ever ride a roller coaster, it's like, why is it so much faster on the bottom? Because you get maximum velocity at the bottom. So let's solve for, what we're going to do is we're going to solve for maximum velocity at the bottom. We're going to use the top to solve for minimum velocity, but still being able to stay in the circle without falling out of the circle. Let's rearrange this equation real quick and we'll get there. I promise. The easiest thing to do at this point is to move that mg to the other side. So I could have, let's see, FC minus mg is equal to m times vt squared over r. Multiply both sides by r, and I get r times fc minus mg is equal to m times vt squared. It's supposed to be m. If I want to divide both sides by m, I would get, let's see, divide both sides by m. So they cancel on the right. So I would have r times fc minus mg divided by m is equal to vt squared. If I square root both sides, I finally have it solved for velocity. Finally. So what I'm going to do is get a big fatty square root symbol. And I'm going to have r times fc minus mg divided by mass, all underneath this, is equal to tangential velocity. There's my equation. Yes, that was a beast to get to. It's something that you could easily do, provided you know the first formula. It's just a rearrangement to solve for velocity. And we did that at the bottom because that's where we're going to see the maximum velocity. Okay. Now, the other question is what is the minimum velocity that this roller coaster could go around and not fall out? Meaning that if you went to Six Flags, they have a green one. It's like on the I-30 side. And you go up, it's called the shock wave. You go up, hang a right, it goes down, it goes in 2 loops. So when you're in the circle, you're not on the circle, you're inside the circle. And how slow can you go so that you go inside the circle and don't just fall out of it, but you actually get to stay in the circle? Okay. So what we're going to do is we're going to come back up to the top and we're going to say, okay, we want to solve for velocity minimum without falling. Out. Okay. And then we can base that off of our formula that says it's FC plus mg is equal to MAC. Now, the circle's not going to change. The mass isn't going to change. But if we wanted to minimize anything to slow it down, what if we were to reduce the centripetal force? So what is the smallest value you can think of for centripetal force? What's the smallest number that you know? You got to unmute.
0.
0. I'll totally take that one. Completely take that one. So if FC is 0, FC has gone to 0. All we're left with, so this guy goes to 0. We're left with mg is equal to MAC. Well, we know that acceleration is VT squared over R. So we can say that mg is equal to m times VT squared over R. Well, the m's, they cancel out, don't they? So that's gone, that's gone. If I multiply both sides by R, I would get RG is equal to VT squared. If I were to square root that, I would simply get the square root of R times G is equal to tangential velocity. So if we're looking for the minimum velocity in order to stay in the circle without falling out, it would be the square root of radius of the circle times gravity. Gravity's 10. So the square root of 10R is the minimum velocity to stay inside of a circle. I think this one will be the easiest one to remember because it's so small. But both of these equations are important. You won't find them on a formula chart. So make sure you find them in your notes and highlight them, mark them, and make it easy to get to. So as we do the practice problems, you can refer to them. If you have any questions that say, what is the minimum velocity? You're going to use the root of R times G. If you're wanting to know what the maximum velocity is, you've got the root of R times the difference of FCMG, all divided by mass, the root of all of that. I'm going to shrink this in so you can see all of it at once. I'll give you a second to just make sure that your notes are caught up. I think I can make it see all at once. But that's what we've done. We've taken Newton's second law that we already knew. We have a new force. It's not new, it's gravity, but it's new for these circles. And then we derived equations from that. Will we ever get a question asking about average velocity with vertical circles or just a min and a max? You could just get what is the velocity. So you can get what is the velocity. And you would just simply use centripetal forces, mass times centripetal acceleration. Then you can break acceleration into velocity squared over r and solve for acceleration. Solve for velocity. Yes, you can get that. If it's going to be about maximum or minimum velocities, you're going to use these two strategies. Don't worry, we're going to do some practice problems together. You'll see what the questions are like today. You'll get a really good idea of what the questions look like today. And your experience with them today should give you enough information to be confident with them. All right, now that you've had a second to look at that, let's do this. Let's switch over to the practice sheet. I'm going to walk you through the front half. It's pretty simple the way it's laid out, but I just want to get you started with it. Then what you're going to have is the second sheet. So I'm going to walk you through the first part of this one. You have this sheet, the uniform circle, circular motion, vertical circles. This one has how many questions total? 6. So you have 6 questions plus the lab to look at. The lab was the one that I have a worksheet and a video that goes along with it. The video is really short, like less than a minute and a half. I try to be very good about editing it down to it just has the important parts. And I made my daughter stay after school to video it, so you can at least like appreciate that there was a freshman standing here when she didn't want to be. So all for you guys. Let's take a look at this problem. Let's do the front of it together. Then I'm going to turn the work over to you all so that you can continue to work and learn from it. Let's see what we have. A ball with mass of 0.025 kilograms. So mass, let's see, let's get a drawing tool. Mass equals 0.025 kilograms. The end of a 0.6 meter long string. So radius equals 0.6 meters. Now it's going to complete 10 circles in 6 seconds. So what variable is it trying to help us get to? What information does that lead us to?
For the period.
Okay, the period, great. Or T was put in the chat, exactly right. Now, if it can do 10 circles in 6 seconds, we want to know how long does it take to do 1. So how long does it take to do 1 if you can do 10 in 6 seconds?
Uh, 3/5 of a second for 1 revolution.
3/5. Tell me what that is in decimals.
0.6.
Points, yes, 0.6. So my T is 0.6. And this is seconds per revolution. I'm just going to put that there so we don't lose what our unit is. And so I think we've listed everything here that's meaningful to us. It says, what is the tension? Well, in this case, tension is our centripetal force. Let's not let that be lost on us. And I'm just going to call it centripetal force just for ease. You could call it force tension. That's totally fine. I'm going to call it centripetal. It wants us to draw a free body diagram for the ball. I don't know the values. This is for scratch work, so the magnitude of the arrows don't matter. If we were turning it in for a test, it would. So be careful with those. We know that we are at the bottom of the circle, so FC would be pointed up, and MG is down. I can go and solve for MG because I know the mass is 0.025. I know the acceleration of gravity is 10. So this would be 0.25, 0.25 newtons is my downward force. It asks me to write a net force equation. So what it's really doing is it wants us to solve for tension, but it's like, hey, do this, then do this, then do this, and you will be there, right? It's stepping us through. That's fine. There's no side, I don't have any forces here in my diagram. So no net force in the horizontal. In the vertical, I would say that it is FC minus mg. Then it tells me to solve for tension. Okay, well, that's fantastic. Well, I know that FC minus mg is equal to MAC. I know that part. And if I'm solving for tension, I might want to say, okay, well, if I rearrange, I would have FC is equal to MAC plus mg. Okay, so if I'm solving for FC, I know the mass, I'm good there. I know gravity, good there. For acceleration, acceleration is VT squared over R. Let's see if I have VT squared over R. Well, I know R, but I don't know velocity. So let me put my thoughts kind of off to the side. I need to get acceleration to solve my formula. So acceleration is equal to VT squared over R. I don't have a VT, but I've got an R. So I know velocity is equal to 2 times pi times R over T. If I substituted this for velocity here, I might have something I can work with. So acceleration is equal to, I'm going to square velocity and divide by R. So I would have 4 times pi squared times R over T squared. Yes, I know you want to say, hey, wait, Mr. Watley, that R is squared, shouldn't it? Yes, but don't forget, it gets divided by that bottom R right there. That's why the square goes away. Okay, so we've got this, and we can solve for acceleration if we want to right here, because we would have that's equal to 4 times 3.14 squared times, what was R? R was 0.6. 0.6 over, what was T? Also 0.6. How about that? 0.6 squared. Okay, I'm going to use my calculator to see what I get. I kind of look at this and I would take like that 0.6 gets rid of that square. I think I might be wrong. Times 3.14 times 3.14 equals divided by 0.6. I'm getting 65.73 for my acceleration. 65.7. Oh, I mean, yeah, for my acceleration. Is that right? Looking at my cheat sheet and see if I can find it. I don't see it up there. All right, so y'all do the math with me. Tell me if I'm getting it wrong. So I'm saying acceleration is equal to 65.73. That would be meters per second square. Who cares? So that means over here, I would have my mass. My mass was 0.025 times 65.73 plus the mass of 0.025 times G, which is 10. When I do that math, I get 0.025 times 65.73 plus 0.25. 1.89. So that's my work on this one. I know my centripetal force is mass times centripetal acceleration. If I'm at the top of the circle, they're going in the same direction. If I'm at the bottom of the circle, they're going in opposite directions. Will FC always be greater than FG? I want to say yes, but what I hate is the word always. Let's just assume it will be unless you find a reason why it's not. Just the word always seems to always have an exception. So I'm very weary of making an absolute statement in physics. I just really am. Okay, now that we have that, let's take a look at the bottom of the page talks about the top of the circle. So I'm going to scroll up so that we can do the bottom of the page, which happens to be the top of the circle. Zoom this back in so I have room to write. So draw a free body diagram for the ball. So we're at the top of the circle. Now I know that FC and MG are going the same direction. We're not worried about the horizontal just the vertical, we would have FC plus mg. And then if we solve for tension, we would say FC plus mg is equal to MAC. And we could say that FC is equal to MAC minus mg. In this case, the masses are the same, gravity is the same. Would acceleration be the same or different than what we just did? So unmute and tell me, would acceleration be the same or different at the top compared to the bottom?
Different.
Everybody else?
I believe it would be different as well.
Okay. Anybody else?
I think it's the same.
So I've got two difference and the same. Oh, I got 2 and 2. Anybody else wanting to weigh in? No, that's fine. Okay, so mute back up and let's take a look at this. Let's scroll up to where we did our work. Acceleration was based, ultimately, we solved acceleration by saying 4. Okay, that's not going to change. Times pi square, that's not going to change. The radius of the circle is still the same, and the period still the same. So our acceleration is the same. Acceleration is the same because it's still 2 pi r over t, all that squared divided by r, right? So it ends up being 4 pi squared times r over t squared. As long as the time it takes to go around the circle is constant, and whether you clock it from top to top or from bottom to bottom, it's still the same amount of time to go all the way around. The radius didn't change. We didn't come further to the middle of the circle or further out. And the acceleration is going to be the same. So we can use that same value down here. And we can say that FC is equal to the mass 0.025. If I got that wrong, correct me. I'm going off of memory half the time. 6573 times 65.73 minus the mass again, 0.025 times gravity. Now the centripetal force is going to be equal to 0.025 times 65.73. Now we're going to subtract the 0.25, which is 1.39. Why do I feel like something's wrong there? Maybe not. Newtons. So the force at the bottom was 1.89. The force at the top is 1.39. Less force. Let me shrink this in so you can see the whole work, all of the work. At least that much of it. So these problems are simply walking us through how to do it. I want you to do the back page. It does the same thing, except from the back page, you're going to have to use your root RG formula. And it's going to basically ask you for that, but it's going to step you on through how to get there. And then just go from there. So there's a little bit on the back. There's that entire other page that had 6 problems and the lab.